For this part of the lab, we chose an appropriate pinhole size to optimize the size of the beam on this without it actually clipping. And then we observed the fringes on the viewing screen right here, took images with the camera. We then used the non-wedge shear plate to check the collimation. So for the second part of the lab, we had a similar setup to the first, only we had a plano-convex lens with the plano side facing the mirror at first, and then the mirror was set up at the radius of curvature plus the focal length of the plano-convex lens away, such that the light coming in was collimated and the light coming out was collimated. To test the collimation, we oriented the shear plate one direction, and such that we tested the collimation light coming in. When it was collimated, all the fringes were all parallel to one another, and they were within the axis of the laser beam. We flipped the shear plate around and retested the collimation. For this setup, we adjusted the tip, tilt, and defocus of the mirror. When defocus was added, the fringes simply were moved towards, were angled off vertically, and then we adjusted the detail. They were angled off again, however they had that slight hyperbole shape to them. And then when you added tilt and defocus together, it was essentially just the same as adding tilt. After this, we moved the mirror to the focal length of the plano-convex lens, and then we flipped the lens around such that the plano side faced the mirror in order to introduce spherical aberration. From then, we tested how spherical aberration is affected when you add tilt, decenter, and defocus.
First, we want to explain the shear plate conventions. In the top left here, we have the physical distance for shear, S, and the radius of the fringe pattern, R naught. In the case of the collimated light, this R naught value should match the radius as the aperture. In the bottom right, we have the normalized version, where delta is the normalized shear distance, calculated as shown in the bottom left. Now what we actually see using these shear plates is a difference in OPD of the original and sheared wavefronts. Here in these equations we see that this OPD is equal to delta W, or the wavefront area difference equation, which is equal to these various values as shown for zero wedge OPD and wedge plates. So now it's good to be familiar with different shearing patterns and the respective aberrations. Here we have straightforward lateral shearing with no tilt inside at and outside focus, and then we have with tilt inside at and outside focus. Basically, it's all straight line fringes, and the orientation depends on the situation. For spherical aberration inside at and outside focus, we see clear bending of the fringing lines, and as we go outside of focus, they more or less develop into a swirling pattern. For coma, we have a distinct star pattern at focus, but once we go defocus, you kind of deviate from that star pattern. For stigmatism, we see vertical and horizontal fringes from the sagittal and tangential shearing. We notice that there is a stigmatism, though, by the amount of fringes at these different sagittals and tangential plane, or shearing, excuse me. In our case, we have more fringe lines in the tangential shearing direction than we do in the sagittal. But we're more likely to expect to see something like this in the lab, the typical S-shaped fringes, and this is most likely due to spherical aberration with a little bit of tilt.
These are the interferograms for the non-wedge shear plate with the best orientation and the worst orientation. At worst orientation, you can see that there is some spherical aberration and tilt. Here is we add defocus. As you notice, more fringes appear as we go further away from focus. As we add decenter, the fringes become slightly tilted. When we use the testing mirror, as we added defocus, more fringes were added just like last time. The wedge shear plate, when we added decenter, you could see that there was a slight tilt. And the reference lens at best focus, this is what it looked. You can see that there's spherical aberration there. And when we were at outside focus, this was our interferogram that resulted. And we were able to find that we had about 12 waves of spherical aberration, a tenth of a wave of coma, and about 14.3 waves of defocus and 4 waves of tilt.